Hi, hello, welcome to Abbhichemistry. Myself Abbhinav and I'm going to teach you all solid state. If you haven't subscribed yet, please subscribe, like and share my channel to everyone. Let's start with introduction. Matter is made up of solids, liquids and gases. The main difference between is the intermolecular forces of attraction. Because of the intermolecular forces of attraction between the molecules, they are very much close to each other. Solids have greater intermolecular forces of attraction when compared to liquids and gases. In this chapter, instead of calling them atoms, molecules and ions, I would like to simply call them as constituent particles. So, if we see anywhere constituent particles, it means atoms, molecules and ions are present. Since the intermolecular forces of attraction is higher in case of solids, they have certain characteristics. They have definite volume, mass, shape. The constituent particles have a fixed position and oscillate about their mean position. They are incompressible and rigid. You can see in the animation below how do they oscillate about their mean position. The solid state chapter is based on the arrangement of the constituent particles. So, how are they arranged? For that, we need to classify solids into amorphous, polymorphs, crystallines. Let's discuss about amorphous. As the name suggests, morph means form. Amorph means no specific form. The constituent particles are arranged randomly, that is, the arrangement is not organized. Because they are not organized properly, so they have no specific shape. The range order is short. What do you mean by range order? It means that arrangement of the constituent particles in the order which is repeated. If the repetition is less, we call it as short range order. There is a picture down below. If I draw a straight line, can you tell me, are there any 4 constituent particles which are repeated or which are connecting to the line? No. This type of arrangement is called as short range order. When you have such type of arrangement of the constituent particles, the melting point will not be specific. It will be in a range of x to y. They do not have a sharp melting point. For example, glass has a melting point of the range 1400 to 1600 degrees Celsius. Now, we are going to learn about second type of arrangement, that is polymorphs. So, what is polymorph? The name itself will give you the answer. Poly means many and morphs means form. The constituent particles is always the same. Example is allotropes of carbon. See, we have diamond and graphite. The constituent particle over here is carbon, but their arrangement has given 2 different forms, that is diamond and graphite. The third classification which we are going to learn now is crystalline. In this crystalline, the constituent particles are arranged in a regular fashion and they have definite geometrical shapes. That is, you can look in the picture which are presenting over. If I draw a line connecting all the constituent particles, you can find that line is connecting these constituent particles which are equidistant from each other. So let's look over here. 1, 2, 3 and 4. So by this we can clearly say that it exhibits long range order. Because it has long range order, it exhibits specific melting point. That is, they possess a sharp melting point because of this long range order. The melting point of salt is 801 degrees Celsius. This chapter specifically explains about crystalline substances. In simple terms, we can call them as crystals. So when we talk about crystals, there is a specific term called lattice, or we can call it as crystal lattice. Now, what is crystal lattice? Crystal lattice means arrangement of the constituent particles in a given space. If you look at the animation down there, you can find how they are arranged properly. This pink box is called as a unit cell. I want you all to look at the picture below, which is written over there as unit cell. What is a unit cell? Unit cell is a three-dimensional portion of a complete crystal lattice which is repeated over and over again. So this small box, which is circled or which is rounded, keeps on repeating itself for a longer time. If you are able to study the properties of this unit cell, I'm pretty sure you'll be able to study the properties of entire crystal lattice, or you can say the entire properties of the entire crystal is easy to. So what is the shape of the unit cell you observed? It's the shape of a cube. There are different forms and different types of unit cell. They are called as Bravais lattices. But we are not going to learn about them right now. And we are going to learn about cube. So let us now understand the dimensions of the cube. The cube consists of 8 corners, 12 edges, 6 faces, each face 2 diagonals, that is 6 into 2, that is 12 face diagonals, 4 body diagonals. Now let us discuss the properties of the cubes. What are the properties of the cubes? It has edge length, which is A. Then half of the edge length, say this is the half of the edge length is equal to A by 2. Half of the edge length is nothing but A by 2. So for face is equal to A by 2. Okay, now let's find out the face centers, the distance between two adjacent face center here and here. We are going to find out the distance of this. Now I'll name it as M, this one will be N, and this one will be O, right? It completely looks like a right angle triangle. So as per Pythagoras theorem, MO square is equal to MN square plus NO square. MO square is equal to MN square is A by 2 whole square plus A by 2 whole square. So MO square is equal to 2A square by 4. So MO is equal to A by root 2. MO is equal to A by root 2. Rationalizing it. So that is multiplying by the same rational number on both the sides. So MO is equal to A by root 2 into root 2 by root 2. That is equal to root 2A by 2. So the distance between two adjacent faces of the cube is A by root 2. Rationalizing it, we get root 2A by 2. And similarly, the distance between two adjacent edges is also A by root 2. And rationalizing it, we get root 2A by 2. Okay, now. So let's discuss about the face diagonal, that is D, A, B. It is a right angle triangle and we also use the Pythagoras theorem. What does the Pythagoras theorem say about D B square is equal to D A square plus A B square. Okay. Now dB square is equal to, dA is nothing but the edge length, so A square plus A square. So dB square is equal to 2A square. So dB is equal to square root of 2A. Okay, now let's find out the cube diagonal, that is CDB. Let's find out the cube diagonal CDB. So it's again the same Pythagoras theorem which we are going to use right now. So CB square is equal to CD square plus DB square. So CB square is equal to, CD is nothing but edge length, A square, plus, and DB is nothing but the face diagonal, root 2A. So CB square is equal to root 2A whole square. So CB square is equal to A square plus 2A square. So CB square is equal to 3A square. So CB is equal to root 3A. So length of the face diagonal angle DAB is equal to root 2A, and length of the cube diagonal angle CDB is equal to root 3A. Please remember them, because in the coming topic you will be using them all. Okay, now let's get back to the unit cell. So unit cell is divided into primitive unit cell and non-primitive unit cell. Primitive unit cell consists of simple cubic cell, and non-primitive unit cell consists of body-centered unit cell and end-centered unit cell, face-centered cubic cell, edge-centered unit cell. The unit cell in which the constituent particles are present only at the corners of a simple cubic cell, we call it as primitive unit cell. Next, non-primitive unit cell, not only in the corners but also at the centers. That's the reason we have edge center, face center, body center and end center. Primitive unit cell can also be called as simple cubic cell. As you can see in this 3D animation, the constituent particles are arranged as if they are arranged on the corners of the cube. Okay, let's discuss right now. See, the one possible imagination for every scientist, let the constituent particle be a sphere. So if we consider it as a sphere, then we have a radius r of one sphere and radius r for another sphere. So r plus r, that is equal to 2r. And this is edge length A, which is same in all direction. So edge length A is equal to 2r. So A by 2 is equal to r. Remember this. Now let's check the contribution of that one atom which is assumed to be present at the corner of a cube. So what would be the contribution right now? As you can see in the 3D animation over there, you can see a blue box in which a constituent particle is there. Now you can see that the eighth part of the particle is present in one cube. The same thing you can observe in a 2-dimension over here, where you can find only 1/8 part of the sphere is being contributed to one cubic cell. The number of constituent particles in a unit cell of a simple cube is represented as Z. It's not the number of constituent particles, number of constituent particles which contribute to the unit cell. Let's see. So contribution of each constituent particle present at the corner is 1/8. Then how many constituent particles are there? 8 constituent particles are there. So 1 by 8 is contributed from each constituent particle. In that manner, there are 8 constituent particles. So the total constituent particle which is present for one particular cube is only one constituent particle. I want you to look over here. You can see this is 1 by 8. This is also 1 by 8. 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 1 by 8 and 1 by 8. So 1 by 8 into 8 is equal to 1 constituent particle. So let's discuss about what is packing efficiency. Packing efficiency is nothing like you're taking a box and that you're putting a sphere. The sphere is so well fit in it that it does not move, nor the box gets pulsed up. It is completely, totally, happily packed inside the box. Volume occupied by the contributed constituent particle by volume of a unit cell. So it has been given a formula, that is Z into 4 by 3 pi r cube. What is Z? Z is nothing but number of contributed constituent particles per unit cell, and 4 by 3 pi r cube is nothing but the volume of the sphere, contributed constituent particle, and a cube is nothing but the length into breadth into height into hundreds, because we need to go for the packing efficiency is calculated in terms of percentage, so we will be going for into 100. So let's solve it. So Z is equal to 1 because it's a simple cubic cell, so Z is equal to 1. So packing efficiency is equal to 1 into 4 by 3 pi r cube by a cube. So 44 by 3, what's packing efficiency now? R is nothing but a by 2, that is radius, as we have seen earlier. So 1 into 4 by 3 pi a by 2 whole cube by a cube. Calculating this, we get packing efficiency, into 100, into 100. Packing efficiency is equal to 1 into 4 by 3 pi r cube, so that will be 4 by 3 pi a cube by 8 divided by a cube. Now a cube gets cancelled, so packing efficiency is equal to 4 by 3 pi r cube is nothing but 22 by 7, pi is nothing but 22 by 7, so 1 into 4 by 3 into 22 by 7 into 1 by 8. Calculating this, we get 52.4. So 52.4% is the volume occupied by that sphere, the contributed constituent sphere. So what is left out? 47.6% is the space left out, that void. We can simply call it as void. The void left out is how much? 47.6%. Body-centered cubic cell, or B.C.C. So what does it explain all about? Let's look at the 3D animation. It has 8 constituent particles in the corner and 1 constituent particle in the center. Contribution of body-centered cubic cell. Look at the animation, and now here we find it here is 1 by 8 part of the corner is being contributed. 1 by 8 part of the corner constituent particle is being contributed to here. So 1 by 8, so 1 by 8, 1 by 8 and 1 by 8. And the center has one constituent particle. Total number of contributed constituent particles in a unit cell of a body cubic cell is denoted as Z. Okay. So, contribution of 8 constituent particles present in the corners, that is 1 by 8 into 8, that is 1 constituent particle. Contribution of constituent particle present within the body, that is at the center, that is 1. Z is equal to 1 plus 1, that is 2. That means there are 2 constituent particles present in a body centered cube. So, the total contribution for one unit cell is 2 constituent particles. Okay, let's discuss the relation between radius and the edge length A. So, length of the cube diagonal is nothing but root 3a, which we have discussed earlier. Now, r plus r plus r plus r, that is equal to 4r. Okay, 4r. So, root 3a cube diagonal is equal to root 3a is equal to 4r, then r is equal to root 3a by 4. Now, let's discuss the packing efficiency of body centered cube. So, it also has the same thing, volume occupied by the constituent particles in a unit cell by volume of a unit cell. So, it also packing efficiency we have, so we need to take it out percentage, so we multiply with 100. Substituting everything in the formula, we have 2 into 4 by 3 pi, we will be using this one, root 3 by 4 a whole cube by a cube. Calculating this, we will get the answer, that is pi root 3 by 8. That answer is 68%. So, 68% is volume occupied by the ears. Then, what about the other 32% is the void. So, now let's discuss about the face centered cubic cell. The face centered cubic cell consists of 6 faces. So, in each face, you have one constituent particle, and on the corners we have 8 constituent particles. So, let's look at the animation. Now, let's look at the contribution of the face cubic cell. So, the contribution explains all about, see, you can see in the animation, there is only half for each face. So, one constituent particle is sharing only half with the other cube. Okay. Now, let's look here. This is half, 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 and here bottom half, half, and back side is one more half, right? And this corners 1 by 8, 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 and 1 by 8. Number of contributed constituent particles in a unit cell of face cubic is Z. So, contribution by 8 constituent particles present in the corners are 1 by 8 into 8, that is 1 constituent particle. Contribution of the constituent particles present on the faces, that is half into 6 faces, that is equal to 3 constituent particles. So, total number of contributed constituent particles are 3 plus 1, that is 4 constituent particles are contributed. Let's now discuss about the relation between radius and edge length in F.C.C. So, we have length of the face diagonal is given right now, root 2a as explained earlier. Now, we have 4r is equal to root 2a, that's r plus r plus r plus r. So, r is equal to square root of 2a by 4, that is equal to a to root 2. Packing efficiency in face centered cubic cell. So, the same formula applies. And the same formula here too, but this time we'll be using this one, R is equal to A by 2 root 2. So substituting in the formula we get, so here F.C.C, so we have 4 into 4 by 3 pi A by 2 root 2 whole cube by A cube into 100, because we are taking the percentage. So you will get the answer as pi by 3 root 2 into 100, that is equal to 74%, means 26% is void. 74% is volume occupied. So here is a total summary of a simple cube, body centered cubic cell and face centered cubic cell, which the volume occupied is 52.4%, 68% and 74%. So volume not occupied will become voids or spaces or holes. This is very important topic which we are going to learn. This is edge centered, the animation of edge centered. And this is end centered. So in this question we have radius given, that is 75 picometers, and the lattice is given, that is body center cubic. He is asking to find out the edge, that is A. So we have the formula, that's R is equal to root 3 A by 4. So substituting it, so 75 into 4 by 1.732. So calculate it and you'll get the answer. Let's solve this question. An ionic compound is made up of atoms A, B, and has a face-centered cubic arrangement. Okay. Atoms A are at the corners and B at the face centers. If one of the atoms is missing from the corners, right? Very good, nice question. What's the simplest formula of the compound? Now let's look at atoms A. Atoms A is equal to corners, so there will be 8 atoms. Now he is saying one of the atom is missing, so one atom. Now how many are there? 7 atoms are there. 7 atoms. Now he is saying face centered cubic. So face centered cubic means 7 into the contribution of each atom in the corner is 1 by 8. That is equal to 7 by 8 atom is present. Now let's look at the face centers. Atom B is present in the face centers. So atom B is now atom B. Where it present? Face center. Face center means 6 faces. So 6 into contribution is half. So 3 atoms are present. So 3 atoms are present. Now A is 7 by 8 and B is 3. A is to B. Now the formula would be A 7, B 25.